Hello and welcome to the Dlubal webinar about advanced steel design using RFEM. My name is Walter Rustler. Today we will see how to model steel details in RFEM. We'll also talk about meshing options that we have in RFEM, and then we will take a closer look at the elastic and plastic design capabilities inside RFEM and the additional modules. When designing elastic and plastic models for surfaces in RFEM, we need additional modules. The main modules that we need are RF steel, which is a stress analysis, which compares existing stresses to a fixed allowable stress. We also need RF mod NL, which gives us nonlinear material model capabilities, and this is required for a plastic design. If we talk about stability analysis, we need additional modules, RF stability and RFEM. We can then do a analysis against buckling, and we can do this in elastic and plastic way. The procedure is to first have a linear analysis in RFEM for a surface model. We need then an imperfection, and the imperfection can be derived from a buckling mode that is calculated in RF stability. We scale this imperfection mode to a certain size and use the imperfect model then as a basis for a nonlinear analysis and stress analysis. And we check then if the stresses are below the limit stresses. Important is that we use a nonlinear analysis for this check. We will see this in the live demonstration. During the live demonstration, you have the option to ask some questions, and my colleague Robert Vogel will help me to answer those questions, and you can type the questions in the little toolbox you see in the webinar software control panel. In the live presentation, we'll take a look at a part of a frame, steel frame, and the steel frame could be something like this. It consists out of a tapered column and also a tapered part of the beam. And we do not model as a surface model the entire frame. We could do it, but it would of course take a longer time because we have more finite elements to take care of. So we isolate the part of the structure, and it is in this case the column and part of the beam of the tapered beam. In general, you will not find an analytical solution for checking against local buckling of such parts where the bending moment has to be introduced over a corner of a frame into the column. Analytical formulas for plate buckling are available, to my knowledge, only for rectangular plates. If we have not a rectangular plate or a certain type of supporting of the rectangular plate or a certain type of stress introduction into the shear or buckling panel, then it is better to do an analysis within a finite element software. I now change to the RFEM software, and we start with modeling the structure. In order to make this a little bit shorter, I have already prepared part of the structure, which is the column, and we see here the column consists out of actually 3 different types of plates. The web is an 8 mm thick plate, and then the flanges are made from 50 mm, and the end plate here is a 12 mm plate. We need now to model the beam that, or the part of the beam which is also tapered. We can do it in different ways. One way I can show you today is to extrude lines into surfaces. I select the lines and I go then to extrude line into surface. And when I do this, I get a dialog where I can set the material for the new surface. I can set the, first of all, I set the direction, which is the global axis C, and I see a little preview of the surface, and the length should be, in this case, 1.5 meters. The thickness of the plate should be the same as the end plate on top of the column, which is 12 millimeters. And with this, I can just press apply and I create a couple of surfaces. Next, I'll create the end plate of the beam, which is now in direction plus C, and the length is not 1500 but 600 millimeters. The thickness should be, let's say, 25 millimeters. On apply, I get also this part of the structure. And I also can go back into minus X direction. Maybe I choose here 1 meter length and again 12 millimeters of thickness. On apply, I get my flanges and the end plate created. What I'm missing now is the connection to the bottom part of the column, and I can do this if I would have here a connection node, or actually I want to have it on a certain distance, and the way I can do it, I can just create a division point on the lines. For this, it is important to know that the lines are modeled from bottom to top. And I can just select the lines, right mouse click on one line, and choose the command divide with distance. I want to divide it from the top, it is from the end, and I choose here 0.794 millimeters for example. On OK, I get here the division points. Next, I can select the end points of the surface and just drag and drop them, and they will snap to those other nodes. So this way I have the taper here very quickly modeled. Next, I need the web. I can just simply select the boundary lines for the web. Thickness should be 8 millimeters. Again, it's a standard plate element, and I just select the boundary lines. Okay, this way I created very rapidly this beam part of the model. I'd like to point out a few other things before we go on. In the display tree here, I can show the surface axis system. And when I show this, I see here there are some irregularities. This is important if you do steel stress analysis in such models, because all the stresses will refer to the local axis of the plate system predominantly. So if I have different orientations in these local systems, when I show different stresses, I will see inconsistent stress diagrams along the surfaces. Because if I say, for example, I want to see sigma x plus, which is on the positive side of the local z-axis of the surface, then I see different values for both surfaces here. So because the plus side on the left part of the flange here is upwards and the minus side is downward. So if I want to see the stress on the outside of the flange, it's a good idea to reverse the local axes so they match. For this, I select the surface and use the option Reverse Local Axis System, and then the axes are identical for both parts of the flange. Here I can do the same thing and click, right mouse click there, Reverse Local Axis System. And the same thing I will do down here. I'll make the model in such a way that the local axes predominantly go downward. Reverse Local Axis System. Here there's another specialty, because in the longitudinal direction of the flange we have the y-axis and not the x-axis. This is because the lower flange is not horizontal and it's a little bit out of the plane. How can I fix this? It is possible. For this I can use following option. I double click on the surface, I go to Axis, and here I find Axis for input. Default, the software chooses the direction. I can rotate it by a certain angle, or I can use axis and I can point to a line which will give the direction of the axis. So I pick, for example, the center line here. OK, and on OK the axis system is moved to the center line, but it's still wrong. The reason for this is it's because the line also points in this direction. The same as the surface, I can click on the line and I also can reverse the line orientation. And now it's in the direction I want to, and I can do this same thing for the other part of the flange. Axis, pick the template and click OK. It is important that you can check this. This way you also can, for example, model circles or circle surfaces, and the local axis system will follow the perimeter of the circle or the radiant of the circle. It is an important feature if you deal with such structures. Okay, let's check the web also. We have here the plus C direction of the beam and the column are different, so I do the same thing again for the column. Okay, now when I look at sigma x on the top flange, I get the same result for all the flanges, and I don't have to think which part of the structure I look at. Okay, I'm done with this, and I can hide the axis system again. Okay, next I'll need some supports. At the base of the column, I'll model a fixed support, and I can do this simple if I use a type of support hinged and assign this to all the lines at the end of the surfaces here. So because none of the lines can move neither horizontally nor vertically, it creates some kind of a fixation. Also, I need some lateral support. So I assume the knee here is held by some bracing in longitudinal building direction, and maybe some purlins are there. So I create a new nodal support that acts only in y direction, and I assign this to the center here of the top of the column. And also at the end of the haunch here, there should be some rotational restraints. So I have a fork type support basically that is horizontally and kind of holds the beam against rotation. If you find the support symbols too big, you can right click on it and decrease the size, or you can change it also into on the right click in the display properties. Okay, one more nodal support I put here on the compression flange of the column to stabilize the column, and it should be of the same type, only horizontal in Y direction. I do this for one reason, to make it happen that we have here then later on when we do stability analysis a local buckling as the first buckling mode. Not in every case we have a local buckling of the web, depends on the thickness of the web and the flanges and etc. Okay, the model I think is so far okay. Maybe to give you a better idea, I can show some dimensions. We have here the depth of the beam here is about 1 meter. So when I take a look at the distance from the center node here to the edge, we have 2 meters. So if we introduce here a load, a vertical load, it will create here a bending moment, the amount of the load times 2 meters. So we have some idea what are the forces that act here. The entire column is about 7 meters in height. Okay. Also, I need to talk now about loading. We need to apply some load. When I do the loading, I could also add here some beam elements and then model the rest of the frame, for example, as a member model, and then put the loads on the members, and the loads would be introduced automatically through the member. But I do here now a individual loading with a vertical load. Typically what you should not do is to introduce the load on one finite element point node. So it's better to distribute the load along the depth of the beam, and the length of this center line here is 600 millimeters, just remember this. And if I want to introduce a bending moment of about 360 kilonewton in the center of the column, I need approximately, because we have here 2 meters, approximately 180 kilonewton of force here in the end of the beam. So, and now if I want to do some kind of parametric analysis, I could analyze it, 180 kilonewtons divided by 0.6 meters, and I would get the value. But I have to do this each time I would change the force. I show you how we could do it a little bit more elegant in the software. First, I create a new load case. It should be without self-weight, and it should be geometrically linear static analysis. I call it design load. And let's assume in this load we have all safety factors and everything is in there. Linear first order theory. In this load case, I create now my load, and I create first a parameter that's called also design load. The unit of this parameter is force, and the magnitude should be 180 kilonewton. Now I will apply this force on this line. So I create a new line load in direction global related to the through line length. And I don't know the value here. I would have to figure it out. But in RFEM you can use the formulas, and the formulas use the parameters that I just defined. So I can use that parameter and multiply it by 0.6 meters. We always use basic SI units, and we see here there is a load of 0.6 meters. That's not divided. We have to not multiply it. We have to divide it, and then there is a load of 300 kilonewton per meter. By applying the formula, this value will be automatically entered here. We see here a small triangle that signals the formula. And on OK, I can assign the load here at the end of the line. If I want to change the load now, I simply go to the parameter, say 160, and if I click OK, the load will change. But I want to use 180, so I change it back. Just as an idea how RFEM helps you with such kinds of problems. Okay, before we can run the analysis, we'll need to talk about a finite element mesh. You find it in Calculate Finite Element Mesh Settings. The important parts of this dialog here are A, the target length of the finite elements. It's set here now to 50 millimeters. It can be changed to any size. This will be the target length, and RFEM will try to make finite elements with the mesh length no longer than 50 millimeters. I'm not pointing out all the details here for this dialog, but I point out the most important settings. First of all, we can have some influence on the shape of the finite elements. They can be only rectangular, or we call them quadrangle. They can be triangular only, and they can be a mixture of triangles and quadrangles. We found that this mixture is giving us the best results. Triangular meshes are not necessarily lower in quality. It depends on what type of elements you have, and some surfaces cannot be created with just rectangular mesh shapes. So for us, this seems to be the most practical way. But however, if you want to, you can select different settings here. And also we try to use identical squares or rectangles where it is possible. The software decides whether to use a triangle or a rectangle on the relation between the lengths of the two diagonals. So first it creates rectangles and then checks the diagonals, and if they exceed a certain ratio that you can set here, it will make triangles. So you have an influence also with this parameter to make it a little bit more or less rectangular or triangular. We can check the option that we will update the mesh each time I click on OK. If I change something, the mesh will be automatically created. On OK, I create the mesh, and we can take a look at the mesh. First of all, I have to show the mesh, which you can control here in the display navigator, finite element mesh. And we see here there is a significant amount of mesh cells along the depth of the beam and the girder and the column, and we have two elements along each side of the flange, which might be a little bit low, but if you want to, you can change it. You can make a finer mesh overall, or you can double click on each surface, and you have here FE mesh settings as well, and you can have a so-called mesh refinement on each surface. If you want to, you can make it finer. If I do this once here, click on OK. Only in this surface we will have a finer mesh. And once I create the finite element mesh, or I click on OK, it takes a little bit longer now to create that mesh. And of course, you have a very fine mesh here now, and the transition from the rough mesh to the finer mesh is done here over certain cells here of the mesh, which is well, better. So we have some smooth transition from the coarse to the finer mesh. This will create, of course, a longer calculation time, and you should think about whether you need a real fine mesh or whether maybe you can get by with a coarse mesh. This depends really on the structure. In generally, we say you should have maybe 4 to 6 elements along such a surface of interest. If you don't really have detailed interest in the results, you maybe get by with a more coarse mesh. I will delete this surface mesh refinement and stick with the regular mesh that we have here and create this one more time. Okay, I think now we are ready to run the linear analysis. By the way, I have here 4 different thicknesses, and I show the panel of the thicknesses in this structure. With the fuse tree, you can here activate, actually I wanted to show the display tree. With the display tree, you can show here the colors in the rendered structure by surface thickness. By default, we have here materials, and the scale will be gone. But if you have here surface thickness, you see here the colors, and you can check whether everything is correct. Also, you can check whether the plus or the minus surface side gets also different colors. You can check it as well as here. It's a good thing to control structures if they have different orientation. The plus and the minus side will have different color. Yeah. So you see here that, for example, the web has all the same orientation. If you look at it from the other side, it has a different color. So this is also a good way to control if everything is correct. We stay with the thickness maybe. All right, to run the analysis, I just simply say here, show results, and it will start the analysis. Now we have, I forgot to tell you, we have steel as a material, and it's linear elastic. What I see here are, well, I see here first a new result navigation tree that starts with deformation, and I can check if my results are okay. I can hide, for example, the load. Hang on, decide, hide my loads, okay. And I can see if everything is symmetric. So there should be no deformation in Y direction and in X direction, of course, but everything looks good. I also should take a look at my basic forces, like I have bending moments, and that should be also symmetric. I have bending moments the other direction, and I have axial forces. And if I have everything correct, then I get a nice symmetric view. This is a good way how to control if your input is correct. Yeah. Also here, if I have a force downward here, there should be tension. So orange, if I look here, it's positive, so it's tension. Blue is compression, so it looks to be okay. Same way is with the stresses. I can go down and I can show sigma x, I can show sigma y on the positive side, for example, sigma x, and sigma x on the negative side. So there are different values. If I go here, there should be it should be visible, and it's important to have the directions correctly. Important is also maybe to look at the equivalent stress von Mises. If I look here, I get a nice smooth display of my equivalent stress. But I only see the existing stress. I don't know, do I have stress over the yield strength, for example. To do this, I'll have to take a look at RF steel surfaces. Inside RF steel surfaces, we can check against a limiting stress. It's quite simple module. We have the ultimate limit state design case, and we check here our design load case. I could do also deflection, so it will check some deflection, but in this case, deflection is out of scope. So I see here all my materials and my yield strengths for different material thicknesses, which is also important because if you work with thick materials, you can have different yield strengths for different thicknesses. The surfaces are listed here, and with this I check the details. In the details I have options to set the individual stress types. I can check my limit deflections for the serviceability limit states, and in the options I have the options to say the important things are distribution of internal forces, and it's set to continuous within surface. I will come back to this point later. Maybe because I read it here, one important thing results in FE mesh points and grid points. There is an important thing which I have to show maybe after I go back to RFEM. Let's first start with calculation of the stresses and comparison to the limit stress. I run the analysis and I see here now I have shear stress, main stress, positive side, negative side, medium or membrane stress, and equivalent stress, which is exceeded by a ratio of 2.67. And you see here also, if I click here where this exceeding part is, typically it is now here where we have this compression point. Okay, so let's take a closer look at this in the graphics. And we see here, actually this is the stress. I have a different tree again here in the RF steel surfaces case, where I also can show the stress ratio for sigma equivalent. And I see here everything that is above 1 is really dark red. And here we have some problems, some local overstress that I need to take care of. But I was talking about grid points and mesh points. It's important to know that each surface has also an overlaying grid which can be controlled also for each surface. It's set here very coarse. It's good to have, for example, if you work with concrete plates that are wide in dimensions, and you can then control the output of the numerical values by grid points or by mesh points. In RF steel surfaces, I have also the option to set, do I want to see grid points or mesh points? If I say grid points, I have to recalculate and there will be less points. So mesh points is a good idea for such small dimensions. And also here I have the option to result in mesh points and grid points. So this is why it's there. If you want to reserve some capacity of the material for other things, you can reduce the allowable stress ratio to 0.8, 0.6. By default it's set to 1. Okay, so now we have the problem that we have some places where we have too much stress. So what to do with it? We'll do a plastic analysis. So this is the stress ratio. And how can I do it? For this, I go back to the material table, and in the material table, or you can also do it in the data navigator here, you have here materials, and you can edit the materials as well here. You have here different material models. By default, RFEM comes with the isotropic linear elastic material model. And you can also use the orthotropic elastic 2D material model. All the other material models are part of RFMAT NL, which is an additional module that will set free those options. And there is an isotropic plastic 1D model, which is for plastic analysis of beams 1D elements. There's an isotropic plastic 2D 3D material model that we'll take a look pretty soon. There's an orthotropic elastic 2D model, which allows you to have different stiffnesses in two different directions on a surface. There's an orthotropic 3D model, which is a more advanced model for 3D and which has orthotropy in three directions, as X, Y, and Z. And the same thing is also possible for plastic design. An interesting thing for steel design is also isotropic thermal elastic, which allows you to set different stiffnesses, different elasticity moduli for different temperatures. So if you have a heated structure, the material gets softer. We have isotropic masonry 2D, which is for masonry, and it excludes the tension stress on masonry and allows only some bending stiffness. What is of interest for us in the steel design here now is isotropic plastic 2D 3D. We have to delete the results, which is clear because we changed the material model. And in this model, we'll refer to the von Mises stress. It's a plastic design approach. So in each iteration step, we compare for each finite element mesh cell, we compare the existing stress to the yield strengths. And if it is higher, we will choose the stiffness in a certain way. So the stress will then redistribute over several iterations into the neighboring finite element meshes. The yield strengths will be entered here. It's set now to as 235. We have a bilinear model in this case, so we can model some strain hardening above the yield strengths. You can also use a diagram. The diagram in this case is identical for tension and compression. As a simplified model for trying things out, you can do a linear elastic only, which is the same as we had before. I use the basic function with a yield strength of 23.5 typically for such cases here. Okay, another material model, this was for von Mises stresses. Another material model that is interesting for steel structures in this type is the nonlinear elastic 2D model, which is similar to what we've seen just now, has the similar options, the same options, but it can behave also differently in compression and tension, which the other model cannot. And also it refers to the principal stresses. If you use the von Mises stresses, there can be situations where the principal stresses are higher than the von Mises stress. So you do not get the worst situation, I would say. But it depends on regulations that you have to follow, which type of stress you have to check. I use this model now, and I use the basic function with a limit, a yield strength limit of 23.5 kilonewton per square centimeters. Okay, since all the surfaces use the same material, all the surfaces can now yield. Okay, let's take a look maybe at the results, and I calculate this first load case nonlinear now. You will see there are some iterations now. First of all, we see here load incrementals, and we see different iterations because we have to check in each iteration what is the yield strength in each finite element mesh and how we have to change it. It's also a good idea to work with load increments because you gradually load the structure and yielding starts gradually at the worst points and spreads then from there. If you have a large yielding area and you apply the load in one step, it is kind of, we call it sometimes called shock for the structure because there's a big change in the strength of the structure and in the stiffness of the structure, and it can lead to not so good convergence during the calculations. Yeah, what we see here now is again the equivalent stress max von Mises. And we see here it's still quite high. It's not 23.5. What is the problem? I have to explain a few things. First of all, we change for each mesh cell, we change the stiffness. And therefore it is not a good idea to smooth the results, that what we do by default over all surfaces. And RFEM has a way, some specialty how to display results. In generally, you get rough results and you want to smooth them over one surface. But when we look at the plastic design and we change only the results per finite element mesh with one, let's say, elasticity modulus, then we have a constant stiffness over the mesh, and we cannot look or change the stiffness over the mesh in each point. Yeah? So therefore, we have to take a look at the results constant per mesh. We can do this here with surfaces in the display navigator under results, surfaces, distribution of internal forces, stresses, continuous within surfaces. So I mesh it, I smooth it over each surface. I can say non-continuous. You see there's a little bit of difference. Maybe I change the smoothing. And I can say constant. And if I go to constant on element, you see here that my stress is not red anymore. Maybe I have to show this also in the result navigator a little bit different. In the result navigator, I have the same trees as I have before, but I have additionally also criterions. Criteria, and one criteria is the design ratio here. Because we have a yield stress, we can compare existing stress to the limit stress. And here we see we have here now utilization ratio 1. We see here also with the non-linearity rate where we have some yielding that happened. And we should also take a look at the strains. And the strains should not be larger than 2%. So once the material yields, the force will stay the same inside the material, but I can kind of elongate it as long as I can, but the strains cannot be unlimited. So in general, the limit is 2%, so 0.02. And we here have no problem. We are far away from that. Okay. Design ratio is clear. And we can take also a look at the real stresses. And there we should have now only stresses that are below 23.5. And we see that's here the case. Maybe to explain a little bit more about this smoothing, I can display here again the different options, but I also show the results. I show the result values, not the extreme values. I want to see everything. On grids, design load, on grid in FE mesh points. So now we see here, if I look for each cell here, I see there is one value for each surface. If I go back to display and change it to non-continuous, I will see I get, takes some time, I get for each finite element, for each connecting mesh cell, I get one value because I have 4 elements in this case, I have 4 values. And they're slightly different. So these are the values that I get from the calculation. But nobody wants to work with such values. That's why we smooth them. In generally, we smooth them. So within each surface, we make it, we make the average of all 4 values and display the average value. If you talk about stresses, we cannot go over the surface edge because stresses are different when there's a different thickness. And if I smooth over the surface edge, I would make a mistake. This is why here are 2 values, because we have different thickness here in the flange as we have in the web. If I smooth continuously total, then I get 1 value also here, but the results are, you know, there's a thick material, I have low stress, and there's a thin material, I have high stress, and make the average, which is not correct here. I have to stay within the surface, and this is why continuous with surface is on default, and which is good in this case. For elastic design, if I do plastic design, I have to look at the constant on element results always, and I get a averaged value for each mesh cell. So it's also important to know that, I hide the values again, that in that case the mesh might have to be a little bit more finer when I do a plastic design, because I can then in a smaller grade change the stiffness on the structure. So therefore, in structures like this, or where there's some kind of points that are difficult, I can also introduce another mesh refinement for a node. I create a new one on this node. I create a rectangular or circular refinement, and by default RFEM creates a radius 5 times the global target length of the mesh, and the outer length should be the target length, which is compatible with the other mesh, and the inner length is 5 times smaller. If I do this, I have to erase the results and do one more analysis. Run this analysis, and then we continue with the buckling check. Okay, load increments, one more time, I explained already. I have to show you where I can set those options. Those are in the calculation parameters. You can set increments. It's by default, I think, set to 5. If there is problems with convergence, you get a message and you can change it. If not, maybe you can stick with less increments and increase the speed of the calculation this way. Okay, we're still okay. We have for mesostress 20.85. Also in the RF steel module, if I go there, I can start it here again. I can, as I showed you before, I can set those values here constant on elements. So also here, here's this setting. If I calculate it, I should get same results, and the utilization ratio is 1 in this case. Okay, great. We are done with stresses. Everything is fine, and we don't have to do anything. Well, we haven't looked at stability yet. It's a very slender structure, and when we look at stresses, we have no check about buckling, about local buckling, flange buckling, web buckling. This is not checked. How can I do this? As I showed you in the introduction, we need to have an imperfection. We need to scale the imperfection to a certain way, and we need to have a certain shape of the imperfection. For this, I use the module RF stability to create shapes and to find out the critical buckling load actually. RF stability can be started by double-clicking on it, and by default I analyze 4 eigenvalues. This should be enough. I have to enter a load case as a basis for this eigenvalue analysis. I need the axial forces in this eigenvalue problem to find the eigenvalues. And I have only one load case, so I use this one. It's the one basically that I want to refer my critical load factors to. I can run an eigenvalue analysis, or I can also an incremental load analysis. That means I run a nonlinear analysis inside RFEM and gradually increase the load until I get the instability message. The difference is that I also take into account force or stress redistributions during the iterations, failing members, and all those things are taken into account, while the eigenvalue analysis takes the axial force level from this load case, the stiffness matrix from this load case, and runs the eigenvalue analysis based on this, and there's no redistribution. Those are actually the 2 important features here. You can choose between Lanczos, roots of characteristic polynomial, subspace iteration method, which is also very common, and there is another iterative method, which is the ICG method, which is less demanding on memory but also takes longer. Okay, with this I run the analysis and I get 4 eigenvalues after a short time. I get the critical load factor, which is a name, or which is a number, a figure that tells me how far I'm away from an instability status. I can increase the load 1.4 times, and then I get this buckling mode that is displayed in the back. And then there's a second one and a third one, and so on. And this factor shows me that there is some danger, and I have to do a nonlinear analysis and maybe also take into account local buckling. Okay, let's take a look into the full graphics. And here we see the first mode. And the first mode is this buckle here, and you have to check the lowest eigenvalue modes and do a nonlinear analysis on an imperfect structure. So I will use this buckling mode to do a nonlinear analysis, and I need to create an imperfect shape from this. How can I do this? I go to the module RFEM, and in RFEM you can create imperfections. You can make a predeformed initial model. It will stretch or change the finite element mesh according to a deformation of an RFEM load case, or according to a buckling shape from the module RF stability. And I choose the first buckling shape, which is what I see here. Now I need to scale it, and I have the option here to enter a ordinate for the scaling. So I multiply, I scale it to 20 millimeters in this case. I'll tell you in a second why 20 millimeters. A buckling shape is normalized or standardized. That means it has basically no direction and also no size. And by this ordinate, I give the deformation a certain size. I get this as numbers, and I can look at it also graphically. Actually, if I want to show it on the other side, I put here a negative value and it's scaled with to the other side. So this is just an optical thing, but it's maybe the way how I'm used to work. So this buckle here is now 20 millimeter deep. It's shown emphasized, so the buckle of course is smaller, but it looks like this. And why 20 millimeters? In Eurocode, for example, you have to scale the buckle in a reference to the length of the buckle. So for example, if you have a beam supported on both ends and you want to have, and you can imagine the curvature, so if it would be a beam, you would use something like length divided by 200 or length divided by 150. Actually, if you use the Eurocode 3, also EN 1993 1.1 minus 5, you find here some hints how big those buckles have to be. And if you use a plastic design, it should be 1/100 of the reference length. And the reference length is the distance of the edge of the buckle, I would say. I can measure this here by using the measuring tool, distances between two nodes. And I can estimate here from here maybe to here. And the distance is about 1.9 meter. So roughly I figure 2 meters divided by 100 is 20 millimeters of scaled value. I also could say I use this distance and would have a less scaling, but there is a little bit of discussion like how to do this and which values to take into account. So I'd rather go a little bit on the safe side and make the buckle a little bit deeper. Okay, I have now my imperfect shape. How to apply it into the analysis? I copy the load case, so I have a comparison. Copy load case to load case 2, and I call it with imperfection. This load case, now I edit, and in the calculation parameters I could apply second order analysis, which is a like more simple full analysis, higher order analysis, which is of linear nature actually, or I can also use a little bit better analysis, which is the large deformation analysis, which is based on a Newton-Raphson iteration, and it also it gives a little bit better results once you have more correct results once you have strains, larger strains and larger deformations. So I have it available, so why not use it? And also I activate extra options. And when I do this, I get a new table here. And in this table, I can activate generated imperfections from add-on module RFEM. And I choose the case that I have defined there. So when I run now the analysis, I'll apply the imperfect structure and I do a nonlinear analysis on this imperfect structure. Okay, let's run the analysis and calculate it. And now we will see again a little bit higher amount of iterations. And you can follow here also the displacement scheme, and you see here that iterations will be more as closer we get to the highest load level. Again, I chose 3 load increments. Depending on the structure you're doing, you might need a little bit more or less. Okay, then after a while I should get some results, and we will take a look then again at the stress distribution and deformation to see if we really applied the imperfect structure. So you see it's more iterations because there is probably some more yielding going on because I have not a perfect structure anymore. And if you have a lot of finite elements, it can be a time-consuming thing, and it's also, even with today's calculation options and computers, it's not so simple to analyze a 3D building, for example, in such a way. Okay, we see here now a different picture, not so much symmetric anymore, and we see here the sigma max von Mises. And we see here a lot of red, which is, now we see the stress, which is below 23.5. But we see here a lot of dark stress, and we see here that there is, similar to my imperfection, a lot of plastification, or it's close to plastification. Let's look at the criterion. Design ratio is here close to 1, and we can use a nonlinearity rate, and we see there is some yielding going on in wide areas of this web. Also, we should again check the stresses, and they are now also higher and almost above the limit what we allow. And this here is a very slender structure, so I don't know if we should really build it in reality and do some more stiffening. But the principle like this is, it's good for showing the principle how we do such design. And now you can, based on this, you can decide whether you introduce more stiffness, whether you change the web thickness, and so on. Maybe we also take a look of this load case, take a look in the direction of deformation of direction y, and we see here it follows the buckle that I have defined as pre-deformation. So it seems to be right, and through this imperfection we get an extra bending moment and extra stresses into the structure. Okay, this is the principal way of how to do such a design. As I said, if you have other buckling modes that are close or just above 1 or below 10, you should consider also those imperfection modes and make different cases of imperfection and check if everything is fine. It could be that in even higher buckling modes we find instabilities because of yielding. We have a high nonlinear effect, and it could be that the model is not stable anymore. So you have to check several buckling modes. Okay, this is what I had prepared for you to show today in this webinar today, and I'd like to continue with the PowerPoint. I know that Robert is answering many questions, and maybe there is time also to talk about a few questions before I end the webinar. And maybe I take a look what we have here. There was the questions like, where can I set the increments of the iterations, the load increments? I go back to RFEM. You can do this here in the calculation parameters. And here is a setting. You can do it for load cases or for load combinations. And here it sets to 3 or to 5 for load combinations, for example. Because we have an iterative analysis, there is also a maximum number of iterations that has to be set here. It's set to 100. So if you reach that limit, you will also receive a message that there is not fully iterated. Also, maybe if you have non-linearities like material models, you can disable them here in the calculation parameters. This is maybe helpful if you have instability and you want to know, is the instability caused by a material nonlinearity? You can deactivate it for some time, for some trials. Also, you can set here the solver options, 64-bit, for example. Some may ask, what is the plate bending theory behind RFEM? There's Mindlin and Kirchhoff that you can select here. Yes, I think those are the most important options here. There was also a question, can I also model bolted connections? I have shown this in previous seminars. Please refer to the website. On our website there are the recordings from the older webinars, and there are some about steel connections. Often you have contact elements that are needed for such models. So you have two plates that are pressed together by bolts, and if there's tension they might form a gap. So with contact elements you can do this, and contact elements are a subset of solids that we also include inside RFEM. And they are in the standard version. Which material models are in the default RFEM version and which are in RFMAT NL? In the default version you have the isotropic linear elastic and the orthotropic elastic 2D. All the other models are set free if you have RFMAT NL. Then there was another question, what about post-critical analysis? Can you handle a snap-through problem? In the calculation parameters, not in the calculation parameters, in each load case, if you edit a load case, you have here the option to set geometrical linear, second order large deformation, and post-critical analysis. Post-critical analysis is if for example, a snap-through problem. If you have a von Mises truss and you lose stability because it snaps through to the other side, then it's a little bit difficult for the solver to find a stable solution again of the equation system. And if you have a post-critical, if you have a snap-through problem, you use the post-critical analysis option, and that should help you find this solution. Okay, then there is one more question. What about fatigue design in steel analysis? So if you want to do fatigue design, we don't have a specific module at the moment. We're planning to have one, but it's not yet available. But what you can do now is, if you have the RF steel surfaces module, which is part of the RF steel module, you can set here stresses sigma delta. I think they are only available if we have several load cases. Hang on, I'll have to change a little bit. Details. Sigma equivalent, sigma, 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 sigma. You can get, we cannot do a fatigue design, but we can give you the stress ranges. Here it is. I'm sorry, there's a new table, stress ranges. And if you get the stress ranges, that means you get the difference from the lowest to the highest stress, which is a input figure for most of the fatigue design codes. So you need to know the variation of the stress. Is it only compression? Is it only tension? Is it maybe compression and tension? And the stress range is an important figure for this, and we can give this here as a result. So it's possible to do that. Okay, I think this is it with the questions. Before we finish this webinar, I would like to point out our website. On our website, you find a lot of information. Also, we post this information on our social media channels. Please tune in there if you want to. I'd like to point out a few things on the website, mainly the Dlubal blog, which is available here on the right side when you start dlubal.com. In the Dlubal blog, you see here tips and tricks and hints for the software every day. We post some new things, different languages. You can search here non-linear maybe, and you get some hints to this using non-linear elastic material, for example. You can browse through here and get some hints and ideas where to find things. So this is an important thing. Also, you find here downloads for trial versions. Please do not hesitate to download those. They work for 30 days. You can check out all the options. When you work with the trial versions, visit the first step page where you find hints about introductory examples, tutorials, and also hints for manuals, webinars, and so on that you can visit. Yes, and finally, I'd like to inform you about the next webinar, which will be on November 14th, which will be about tips and tricks using RFEM. And I'd like to invite you, and at the same time, thank you for being with us today. Thank you also, Robert, for answering the questions. And I hope you have a nice day and see you again one time on the webinar channel. Bye-bye.